Okay, well, if we're given V naught, Vf, and delta t, the first thing we want to do is try to pair two of these. Okay, well, if we try to pair V naught and delta t, they don't appear in any of these triangles together. We can't use them. If we tried to pair Vf and delta t, same thing. They don't appear together in any of these triangles, so they aren't related by this definition, by this definition, by the property of a straight line graph, or by the definition of delta. However, if we have V naught and Vf, we're off to a very good start because we can pair V naught and Vf to get V bar. And then we could pair V naught and Vf as well to get delta V. So, let me grab a piece of chalk, hang on. Now, I already did my underlining when I did the long view of this, but we started with V naught and Vf and delta T. And we combined V naught and Vf to get what? Well, we combined it to get delta V here, we combined it to get V bar here. So now we know this, and this. Okay, so I write that down. V naught and Vf gives us V bar. We can see that. V naught and Vf gives us delta V. We can see that that's going to be true. We'll think about what that means in a few minutes. Okay, but now, what can we do with what we now know? Remember, we don't yet know delta S and A. Okay? What can we combine? Well, we have all kinds of possibilities. And mainly, we can combine delta T with either of these two, and if we combine it with each of these two, we're going to be done. So what do we get if we combine delta T with, well, I did delta T with delta V first, yeah. Okay, so what do we get if we combine delta T with delta V? Well, what triangle does that put us in? From delta V and delta T, we can determine the acceleration. Okay, so we know this and this, therefore, we find the acceleration. Okay, what's left? Just delta S, but if we combine delta T with V bar, we have delta T here, V bar, and delta S in the same triangle, indicating that we can find delta S. So, V bar and delta T give us delta S. So, V naught and Vf give us V bar by the third triangle, and then by the fourth triangle that we kind of sneaked in here, we get delta V, and then delta T and delta V go together in the second triangle to give us A. V bar and delta T go together in the first triangle to give us delta S. That tells us how we're going to be able to reason this out, but, excuse me, it doesn't tell us exactly how the reasoning is going to go. So let's think that through. Okay, how do V naught and Vf give us V bar? Well, V naught and Vf give us V bar by the straight line V versus T graph, which tells us that V bar is the average of Vf and V naught. That's the importance of the straight line graph. Okay, how do V naught and Vf give us delta V? That one should be really obvious. Okay, delta means change in velocity. How would you get the change in velocity if you know the initial and the final velocity? You would subtract the initial from the final. So that's just by definition what delta means. Now, over here, we got to do a little more thinking. Okay, how do delta V and delta T and delta V give us A? Well, this comes, as we've noted up here, from the definition of average acceleration. And we have already thought through the definition of average acceleration and how it gives us this. If we start with the definition of average acceleration and do our reasoning, we find that the average acceleration is delta V over delta T. Average rate of change of velocity with respect to clock time is change in velocity divided by change in clock time, which we write by delta V over delta T. So, given delta T and delta V, we have the numbers to plug in here to get our acceleration. Okay, what about this one? Well, definition of average velocity, average rate of change of position with respect to clock time, by the average rate of change definition, that's change in position divided by change in clock time, and there we symbolize it. Okay, so V bar is delta S over delta T. We're given V bar and delta T. Does this do us any good? Yeah, we're given this and this. All we got to do is find this, multiply both sides by delta T, and there it's going to be. Working through an example where we know V naught, Vf, and delta T. let's say that V naught's 20 meters per second, VF 5 meters per second, delta T 3 seconds, we get V bar. Just following the same order of reasoning that we had here. V bar is V naught plus VF over 2, as we just saw. That's 20 meters per second plus 5 meters per second over 2 comes out 12.5 meters per second. Delta V, second thing that we found here. Okay, delta V is just VF minus V naught, the obvious thing that doesn't really need a triangle, but and VF is 5 meters per second, V naught is 20 meters per second. Subtracting, we get negative 15 meters per second. The negative indicates that we're slowing down. If we start at 20, end up at 5, we're slowing down. Okay, average acceleration comes out to be delta V over delta T, so we divide our delta V by our delta T, and we get negative 5 meters per second squared in a very obvious calculation. And V bar is delta S over delta T. Well, we're going to go ahead and do the algebra. We multiply both sides by delta T, we get delta S equals V bar delta T. And V bar being 12.5 meters per second, as we found up here, we multiply that by the 3 seconds to get our 37.5 meters.